Hello everyone, thank you for joining Mr. Ish for today's video, part 2 on vector algebra. This video will be talking about applications. Just keep in mind everything that we've learned in the previous video, which was part 1, and we're just going to continue from where we left off. Look over here, resultant. Resultant is basically the term which is given to the vector sum of forces. If you remember those examples we provided, diagrammatically we had a vector u and we had a vector v. We used the triangle and the parallelogram methods for determining how the resultant would appear. That's what we're talking about, the resultant. The addition of those two vectors will lead to a third vector. That third vector is called the resultant. And remember, vectors have a magnitude and they have a direction. So all of that has to be kept in mind as we proceed through these examples. Here's one example. If there's a force 1 acting with a magnitude of 55 newtons. Newtons is the unit for force. If there's a force 1, it has a magnitude of 55 newtons. And then there's a second force, F2, and it has a magnitude of 35 newtons, and it acts at a direction of 120 degrees to the first force, F1. And the question is to determine the resultant. How do we go about doing it? Well, technically I didn't explicitly mention that there is a direction to this force 1, but there must be a direction because all vectors have a direction and a magnitude. So arbitrarily just assume F1 is your horizontal line. And technically if we're doing these by diagrams, you have to be careful with the length of these. Remember, the magnitude can be, or magnitude or the length of vectors can be shown clearly by using the length of the segments. Well, assume that I'm showing these things to scale, though I'm not. I'm focusing more here on the math part and less on the diagram. So if this is force 1, which has a units of 55 newtons, and then we have a force 2 acting at 120 degrees, and that is a 35 newtons because there's 35 newtons at 120 degrees. Our goal is to determine the resultant. If you were to use supposedly the parallelogram method, you would draw like a rough parallelogram, and then over here you'd connect, your resultant would be this right over here. What we have to do is determine the magnitude and the direction of the resultant. Think about it. If something is acting at a force direction this way and something like a tug of rope in this, where will the end point be? It will of course go somewhere in between, but we have to determine the magnitude, the exact magnitude and the exact direction of this resultant. So how do we go about doing this? This is where trigonometry comes into play. If supposedly this is my u vector and my v vector, or we can say f1 and f2, I'm going to call this u over here and I'm going to call this v. U, I'm going to denote it as this. It is represented by a magnitude of 55, and now I'm going to put the directions, cosine 0 and sine 0. Remember in the first video I said everything in terms of vectors can be separated into x and y components, the horizontal and vertical components. When we're talking about coordinates, x usually represents the cosine and the y represents the sine. So here I've separated this vector into its components. Here's my magnitude, here's my direction. Look at the v vector, which is the f2. You can write that as 35. You know what we'll put here for the direction, 120 degrees, because we know it to be 120 degrees, and sine 120 degrees. Okay? As we proceed through this example, all of this will become more clear. So we have explicitly laid out the two vectors and their components. All we have to do now is actually calculate the resultant. And the procedure for doing that is not hard. Look over here, you got to open this up. 55 multiplies with cosine 0. What's cosine 0? It's 1. So you get a 55 over here. Remember, we're writing this into vector format. Sine 0 is 0. 0 multiplies with 55, you get a 0. Let's look at this v vector. Cosine 120. Let's bring out the calculator. 120 cosine times 35. I get a minus 17.5 as the x component of this vector, the horizontal component. Look at 120 sine. 120 sine, I get a 0.866. I multiply that with 35, I get a 30.3. Now this is my vertical component of this v vector. You see, I've broken these by means of this trigonometric process into these components. Now we gotta just find the resultant. And the procedure for finding the resultant is add the x's and add the y's. 55 plus 17.5 minus. So 55 minus 17.5 I get a 37.5 over here. See, 37.5, that's the horizontal or the x component of this resultant. The horizontal or the x component. Let's look at the vertical component. 0 plus 30.3. I get a 30.3. The rest is pretty easy. Now we actually have to find this right here. Remember this formula, the actual magnitude? The actual magnitude is determined by the squares of these, the sum of the squares of these, and you square root them. Think back to this formula I showed you. The magnitude is equal to the square root of u1 plus u2, and these were individually squared. So I'm doing the magnitude of r. Take the squares of these and square root them. 37.5 square plus 30.3 square, and you square root and you get 48.2. Our resultant will have a magnitude of 48.2 newtons. 48.2 newtons. But now we have to actually determine the angle. How can we determine the angle? Well, here's a good technique. If you have an x value here and a y value here, which is a cosine and the sine, it's logical to take the tangent of these two, because tan is always equal to sine divided by cosine. You take the y value and you divide it by the x value, 30.3, you divide that by 37.5, then you do the inverse tan of that, and you get 38.93 degrees. 38.9 degrees. Why did I do this? Because look at this. Tan theta is equal to y over x, which is the same thing as sine over cosine of whatever values we're using. Here was my sine component, which is always related to the y. Here's my cosine value, which is always related to x. Therefore, theta must equal to arctan of sine divided by cosine. And you divide these two values, take the arctangent or the inverse tangent, and you get 38.9. So here we have the resultant, which happens to have 48.2 newtons at an angle of 38.9, but from the horizontal. See, 38.9 degrees from the horizontal. It makes sense. What if supposedly F2 was exactly opposite? Then we will basically just have an exact lateral tug of war. And sometimes if two forces are going in the same direction, you have a synergistic effect. If F1 and F2 are both going in the same direction, you will have additive effect. If F1 and F2 are going in opposite directions, you'll have a subtractive effect. But if F1 and F2 are in angles in between, you have a bit of an addition or a bit of a subtractive effect. So you have to keep that in mind. But you can see over here, F1 and F2 have a resultant here, or the resultant is between 55 and 35, simply because you don't have a synergistic effect, nor do you have a complete cancellation effect. It's somewhere in between. So somewhere in between for 55 and 35, based on the forces and the vectors, was 48.2 at an angle of 38.9. Let's look at some more examples. In this example, you basically have an incline ramp upon which you have a certain weight. Let's say that weight is like 75 pounds, and the incline the ramp has an inclination of 25 degrees. The question here is you have to find the perpendicular and the parallel forces of this setup. Like, what's the force parallel to this ramp surface? What's the force perpendicular to this surface if we know that the weight of the object is 75 pounds? And we can assume the pounds here represents the force. These are the types of questions you'll see very commonly in physics. So you have to determine the component over here, which is the weight or the force. This right here is a symbol for parallel, two parallel lines like a railway track. This right here, upside down T, is a symbol for perpendicular, and you have to determine the force perpendicular. So how do we go about this? And everything is parallel or perpendicular to this hypotenuse, this surface. The best way I would recommend for you to proceed with this is like one of those questions where you're trying to determine the horizontal and the vertical components of the forces. One of these horizontal and vertical, one of these components will represent the parallel, one of these will represent the perpendicular. The best way to proceed with this is to draw a second triangle. If this represents the weight that is in question, the 75 pounds, what we do is we have to draw a line perpendicular to this. Why are we drawing perpendicular to this? Because we have to determine the perpendicular force. Connect this to this surface, and now what do we have? We basically have a right triangle over here. We have a perpendicular side, and we have right here the parallel side. Right here, here's my parallel side. It's a right triangle. But if this right here was 25 degrees right here, then this right here is also 25 degrees. And you basically have to find this x component, which is your force perpendicular, and you have to find this y side, which is your force parallel. So how do we do that? You'll do that by using trigonometry. Easy. Cosine, and you know the 75 pounds, the 75 pound weight represents the dimension or the magnitude, you can say, of your hypotenuse. Let's find the force parallel or the weight parallel component, the x component. You do cosine 25 is equal to x over 75. Use your calculator to actually find this. Cosine 25 and multiply by 75. 25 cosine times 75. It's a number which I should round up. I get 67.97. So why don't we just round that up to 68? X is equal to 68 pounds, newtons, or whatever it was, the units. Now to find the component of the vector which is represented by the parallel aspect or the y, you have to use another trigonometric formula. You'll do now here sine 25. Remember, sine 25 is always equal to opposite over hypotenuse. Sine 25 is equal to y over 75. Solve for y. What do you get? Easy calculations. 25 sine times 75. 25 sine times 75. I get it 31.69, but let's round that up to 32. 32 pounds, kilograms, newtons, or whatever it is. So the x component of this 75 pound box weight resting on a 25-degree incline, the x component, which indicates the force at a perpendicular to this inclined surface, is 68 newtons or pounds. For that same weight, the parallel force or the y component is 32 pounds or newtons. You can think of this y component as friction. There's 32 newtons in terms of friction, which is keeping the box from sliding down. Okay, you can think of it as that way. So you can see how these type of questions break a vector into its individual components, horizontal or vertical components, or perpendicular components or parallel components. A very common question in physics. So take a look over here on this screen. This promises to be a very interesting question. Again, in this question, you're looking for a resulting force, a resultant. We will always call the resultant with a capital R. You have to basically look at how the directions are given over here. North 50 degrees west, south 55 degrees west, but you have a magnitude. Each of these vectors has a magnitude and a direction. This magnitude could have been whatever: speed, velocity, weight, mass, pull, newtons, anything. We won't worry about the exact specifics of the magnitude units, but we should be more concerned here about the direction units. Look at this: north 50 degrees west, south 55 degrees west. If you look at this vector u, it says it's 155 north 50 degrees west. So how do we do that? If this is our north, east, south, west, north 50 degrees west will be 50 degrees west of north, right? 50 degrees west of north. So here's my north line. And this vector, which is u, is happening to be 155 magnitude, whatever that might be. Newtons, pull, velocity, that is not specifically important, the exact units. Let's focus on vector v. It says it's 305, but we're not drawing things here to scale. But look over here, south 55 degrees west. If this right here is my south line, this direction is 55 degrees west of south. Look at this, 55 degrees west of south. So this thing over here, vector v, happens to be 305 whatever units. But again, I'm not drawing this to scale. Now we have to determine what the resultant is. You know, if you draw a parallelogram over here and you connect it, your resultant might come somewhere. Let's do it like a rough parallelogram. You can even use the triangle method. Here's my rough parallelogram. Remember, rectangles are parallelograms. My resultant would look something like this. You see, when you connect from the origin to there, your resultant will look something like this. But our question here is to find the exact measure of this resultant. You have to find the exact magnitude and the direction. That's a task of this question. This is where trigonometry will come into play with these vector questions. This is how you proceed. You have to individually write these in terms of their magnitude and their direction. Let's start with the u vector. The u vector can be represented as this: a magnitude, right, with the directional components, cosine and sine. But everything is always measured with regards to 0 degrees, is it not, right? If you have 50 degrees here from north, which represents the 90 degrees, what is the exact measure of all of this? of u, it'll be 90 plus 50. It'll be cosine of 140, and let's create room over here, and sine of 140. Did you see how we determined that? If this right here quadrant is 90 degrees, we're still 50 degrees west of that from north, so 90 plus 50 gives you that 140. But what about the v? The v has a magnitude of 305. Now we have to write the directional aspects in terms of trigonometry. We know we're 55 degrees west of south, but this right here, this is my 90, this is my 0, 90, 180, 270. This right here is my 270 degree. If I'm 55 degrees west of 270, you can say 270 minus 55. It's 215 degrees. So from 0, it's 215 degrees away. And you would write this as cosine of 215 and sine of 215. Now all you gotta do is open it up. You gotta multiply this 155 by this value, 155 by that value, and likewise over here. So when we write them up, we'll get everything in a parentheses. Let's do that. 140 cosine times 155, I get a minus 118.7. There's nothing wrong with getting minus answers here, and I'm keeping everything to one decimal place. Do the same thing with the sine 140. 140 sine times 155. Remember, right now I'm working on the u vector. I get a 99.6. Let's look at the v vector. Exactly the same. Open it up, multiplying with these angle directions. 215 cosine times 305. I get a minus 249.8. Minus 249.8. For the sine 215, let's see what I get. 215 sine times 305, I get a minus 174.9. Minus 174.9. Now we're still in the process of determining a resultant. Remember, the resultant, the triangle and the parallelogram is always addition of vectors, right? U plus v. So keep that in mind. We're doing u plus v. So you're adding all of this to give you your resultant. You're going to add these x components, you can add the y components. So let's add the x components. 118.7 minus plus 249.8 minus, I get a minus 368.5. Minus 368.5 as my horizontal, or the x component, or you can say the cosine component. Now let's add the y components or the sine components. You do 99.6 plus 174.9 minus, I'm using a calculator here, I get a minus 75.3. But this is not just enough. We actually have to find the magnitude. You know, the magnitude is represented by these vertical parallel lines, and the magnitude is always the square root of the sum of the squares of these two numbers. You have to individually square these numbers, add them up, and take the square root. Let's do that. 368.5, you don't have to worry about minuses because the square will eliminate the minus. 368.5 square plus 75.3 square, and you square root it, I get a 376. 376 newtons, whatever units it might be. So 376 is my magnitude of this vector right here. Of course it makes sense. One was 305, one was 155, and they're kind of in the same direction, so there's a bit of an additive effect going on. So it's more than each of these individuals, but less than the sum of those two. All we gotta do now is determine the direction. The direction over here, you have to use a tan. You have to use tan, okay? Let's say tan. The tan is always the y component divided by the x component, or the sine component divided by the cosine component. So what will we say? We'll do minus 75.3 divided by minus 368.5, and this will be tan inverse, right? To give you your theta. Inverse tan of this. Do that calculation, and what do you get? 75.3 divided by 368.5. I didn't use the minuses because the minuses will cancel out, and you inverse tan. I get something called over here theta to be 11.5 degrees. So look over here, we have a minus 75.3 divided by minus 368.5. We inverse tanned it, or tanned it, we got 11.5 degrees. You wouldn't want to be thinking that this right here represents 11.5 degrees right over here. That would be wrong, because it would be totally away from the direction of these two vectors. We would be thinking everything in now with regards to the other horizontal line, which is right here, 180 degrees. It's my other horizontal. my other horizontal indicator, you'll be doing 180 plus 11.5, right? 180 plus 11.5, and you get 191.5 degrees. So you're going to add this to 180 because our next reference horizontal is the 180. You get 191.5 degrees. So the direction of your resultant force is 191.5 degrees. But we have to write this in this format. If it's 191.5 degrees, it's in here in the third quadrant, so you have to determine how far it is from your south. Your two guiding lines are basically either the north axis or the south axis. Here we'll be using the south axis because it's closer to the south axis. So what's my south angle here? It's 270. My north angle is at 90 degrees. So 270 minus this 191.5 I get is 78.5. So this is how your final answer will be. Your resultant here is going to be south 78.5 degrees west. So it's 78.5 degrees in a westerly direction from south. And the resultant here happens to be 376 units. An interesting question, but do not use this as a final answer. When you're given questions in this format, you want to present an answer in that format. So south 78.5 degrees in a westerly direction. We'll look at some more example which is similar to this coming soon, but let's look at something different. Look at this question over here. Supposedly you're a baseball pitcher and you're this guy right here, and you throw this ball in this direction. You throw the ball at a speed. You throw it at a ball at a speed of 80, I guess, miles per hour would be a good speed. I don't know how they measure the speed of balls, but imagine 80 miles per hour, and you throw it at an angle of, let's say, 20 degrees from the horizontal. You know, using this, you can create a diagram. Here's your horizontal. You've thrown something at a direction of 20 degrees from the horizontal. Here's your right triangle, and your speed is represented by this. It's 80 miles per hour. Alright, you've thrown the ball up that way. You want to determine the horizontal and the vertical components of this vector. The vector here of this 80 miles per hour, because when you've thrown a ball at 80 miles per hour, you have both a magnitude and you have a direction. All you want to do is break it down into its horizontal components and vertical components. Remember, horizontal components are usually your x or your cosine component, and your vertical component is usually your y or sine. All you have to do here is using basic right triangle trigonometry to determine the individual components of this vector. How will you determine the x component or the horizontal component of the ball thrown? It would be, and remember, when you're determining this, the horizontal component will represent the horizontal speed of the ball. The vertical component will represent the vertical speed of the ball. Okay, so the horizontal component, h for horizontal, you would say would be cosine 20 is equal to x over 80 miles per hour. You'll solve for that x and you would get, let's bring this calculator here, 20 cosine times 80, you get a 75, let's round it up, 75.2 MPa. In a horizontal direction, your ball has a 75.2 speed. What about in a vertical direction? You would say sine 20 is equal to y over 80. Remember, now you're looking at the vertical component of this ball which is thrown. You solve it out over here. So sine 20 sine times 80, you get 27.4 miles per hour. It makes sense. As the ball is thrown more horizontally, closer to the x-axis or horizontal, as the ball is thrown more horizontally, of course more of that direction is in the x-axis versus the y-axis. Therefore the speed more closely matches the original speed, the vector speed, in terms of the horizontal. If the ball is thrown more in a vertical direction, then this value here would have been higher and this value here would have been lower. Makes sense. So remember, these type of questions will show up frequently in physics. Let's look at this question over here. A very common question you'll see in physics or engineering. You have a certain weight which is suspended from the ceiling by two wires. You have a wire A and you have a wire B. And wire A is attached at 50 degrees, wire B is attached at 30 degrees. You have to determine the tension in this wire A, TA, tension A, and the tension in B, wire B, so TB. The weight is 2,000 pounds. So you have to determine the tension TA and tension TB using vectors. It seems a bit of a complex question, but actually isn't. You got your right triangles You got 50, 30, and you have a right triangle over here. Both of these are independent right triangles. The way you proceed about this system is you assume that it's a static equilibrium. Static equilibrium means everything is holding. Static equilibrium, everything is in stasis, there's no movement. Once you make that assumption of it being static, this handwriting is just not good. Once you make the assumption that it's in static equilibrium, then you have to look at the horizontal and the vertical components. From a horizontal point of view, remember you're always looking at the x-axis and the cosine values. For the vertical component, you're always looking at the y-axis or the sine values. If you look at the horizontal component only, the horizontal component for A is basically A cosine 50 degrees, right? A cosine 50, and it must be equal to what you have on the other side, B cosine 30. That's the horizontal component done. Remember, static equilibrium, everything is in stasis. The horizontal values equal each other. What about the vertical component? Now the vertical component has A sine 50. Remember, we're not looking at vertical y values, we look at sine. Plus, look why I'm doing plus over here, plus B sine 30 minus 2000. Now look, minus 2000 equals 0. Why did I do adding of these two and minusing from 2000? Because if you think about this system, gravity is pulling this weight down, but that weight is being opposed equally by the tension in A and B in an upward direction. Remember, opposite but equal forces. These two are adding up or working together to hold the weight of gravity's effect on this weight. So these two add and this minuses, and the sum of all of these vertical forces should equal 0. Now it's just a matter of simple algebra to solve for A and B. Look over here at this horizontal. You're gonna solve for A. You could have solved for B, but I'll solve for A. I'm looking over here. A is equal to B cosine 30 divided by cosine 50. I'm isolating everything here but A, taking everything on the other side. So look, to calculate for A, you take the cosine 50 on the other side, you do B cosine 30 divided by cosine 50. When you do it on your calculator, you get a 1.347b. Remember, A is equal to 1.347b. So I have a 1.347b over here. I'm going to substitute this 1.347b here in place of A, multiplied with 50 sine and add it to B sine 30. Look what I get. I do 1.347b, 1.347 multiplied by 50 sine. I get a 1.031 over here, B. Then I add that with sine 30b, and I get 1.531. I get 1.5318b is equal to, I take 2000 on the other side. Now solve for B. B is equal to 2000 divided by 2000 divided by 1.5318. I get a 1305. Let's round it up. 1305.6, 1306. I get 1306. The tension in wire B is 1306, and let's give it a unit, newtons. All we gotta do now is determine the tension in A. All you can do for that is plug it right here into this equation right here. You know B is equal to 1306. Plug it in here. Plug 1306 right here, and this B multiply 1.347, and it'll give you your tension for A. So multiply that by 1.347, and the tension in A is equal to 1758 newtons. It makes sense that this A being at a higher angle, 50 degrees being larger than 30, has more of a vertical component, therefore it bears more of the weight of that 2000. Whereas B being at a smaller angle, closer to the horizontal, its vertical component of that entire weight is less than that of A. So the tension in A is 1758 newtons, and tension in B is 1306 newtons. But you can see how the process was involving the assumption of static equilibrium. The sum of forces in the horizontal direction are equal to each other. The sum of forces in the vertical direction, the two wires adding up and opposing the weight, and that sum is equal to 0. You solve for one, you replace, and then you go down the process of substitution and you calculate the tension in each of those two wires. I want to present another one of these type of examples. Basically, the question was something like this. You basically have a river or an ocean in which you have two small tugboats. This right here represents a tugboat over here and a tugboat over here. And they're each pulling like a big barge. The barge is probably 6,000 tons. I don't know how you would weigh a barge. But whatever that big barge is, it's being pulled by two tugboats at an angle from this dead center at 18 degrees. So each of these barges is pulling at 18 degrees from this vertical, a very heavy barge, 6,000 pounds or 6,000 tons. And your goal is to determine in each of these what the tension is. A similar type of question. Now, of course, we have movement over here, but you can assume again there's static equilibrium over here. Static equilibrium, and you can translate the entire picture into something like hanging from a ceiling and you're suspending a weight of 6,000. Now you will see that this question will proceed in a similar manner. In the horizontal or the x direction, the sum of the force is such that you will need these angles over here, because you will need that, because remember, you're always using it with reference to the horizontal. If this right here is an 18, that's a 90, you know what that angle will be. You'll do 90 plus 18 minus it from 180, and you get 72. Remember, the sum of the three angles within a triangle is always 180. Okay, so this angle is 72. So in the horizontal direction, you're going to do the sum of the forces, and this is what you're going to do. Well, let's call this T1 and we'll call this T2. T1 will be multiplied by cosine 72, and it will equal exactly the opposing tugboat, which is pulling, of course, the same weight at the same angle. T2 cosine 72, because look what we end up having here is an isosceles triangle. Two equal sides, two equal angles. If T1 times cosine 72 is equal to T2 exactly the same, you know right away T1 is equal to T2, because they're both exactly equal. Anyhow, that's the horizontal component. Look at the vertical component. It'll be T1, you know, vertical is more to do with sine 72 added by the other tugboat pulling exactly a heavy barge in a similar direction, similar magnitude, T2 sine 72, but opposed by an equal opposite force of 6,000 tons or whatever, and equaling 0, because the sum of the forces in the vertical direction must also equal 0 in static equilibrium. So how do we go about proceeding with this? Substitution is the way. If T1 is equal to T2, wherever you have T1, you can put T2. So look over here. If T1 and T1 sine 72 plus T2 sine 72 are the same, you can just say 2 times T1 sine 72 is equal to, take 6,000 on the other side. Now solve exactly for T1, because whatever you solve for T1 will be the same as T2. Take 2 on the other side, so 6,000 divided by 2, I get a 3,000. Now divided by sine of 72. 72 sine, and I get it 3154. T1 over here is equal to 3154. So the pull of this T1 is 3154. Let's just call it newtons. I like the unit newtons. And T2 must also be the same, because T1R is the same as T2. 3154 newtons. Not a difficult question. Much easier, simply because we are dealing here with an isosceles triangle. When you're dealing with an isosceles triangle, you can make such assumptions like this. Remember, in the previous example, you had two different angles, 30 and 50 degrees. You couldn't make such assumptions, so the process became longer. And we're only asking to calculate the tension, so here it is, easier. Now this will be an interesting question, like a navigation style question. Supposing there's an airplane which is flying at a speed of 580 miles per hour. It is flying in a direction north 30 degrees east. Remember, vectors, magnitude and direction. So this plane is opposed by wind. A for airplane, W for wind. Wind at a speed of 60 miles per hour, but at north 90 degrees west. The first step you want to do when you have these type of questions is to plot them or graph them. So let's draw the airplane, and remember, in terms of diagram, you want to try to make the lengths proportionally larger somehow, but I won't. In the interest of space, I won't do that. So the airplane is north 30 degrees east. So you are going 30 degrees east of north. And it's going to be in this direction. Here's my airplane. And you know it's 580 in miles per hour. That's the airplane. If it's 30 degrees east of north, what does it mean? Everything with respect to the horizontal, it must be 60 degrees. But let's look at the wind. The wind is 60 miles per hour, but it's north 90 degrees west. North 90 degrees west. So that means this right here is my wind. And it is at a speed of 60. What we gotta do right here, and you know, before I forget, if this right here represents my wind with regards to the 0 degrees, it's 180 degrees. See, it's 180 degrees away from 0. So we have our direction over here. This happens to be 60 degrees, this happens to be 180 degrees. And now, the next step, of course, is to write these in vector forms. So for the airplane, you'll do 580, then you'll bring the trigonometric aspects. You have cosine 60. Remember, you're using these to convert these into usable angles. Sine 60. The x component, horizontal component, the y component, vertical component. The wind. Wind is of course 60 miles per hour, but it is at a direction of cosine 180 and sine 180. You know what the resultant is the addition of two vectors. You add them up to get your resultant. We're going to do a little bit of calculation shortcuts here. I'm going to add this with the product of this. I'm going to do cosine 60, 60 cosine multiplied by 580, and I'm going to add it to the product of these two. They'll give me the x component of the resultant. Plus 180 cosine times 60, I get a 230. You could have individually broken these steps out without this shortcut. You could have written all of this again over here and all of this again and then re-added it. I'm not doing that, I'm skipping the step. Now I'm going to do 580 with sine 60 and add that to 60 with sine 180. So 580 times 60 sine plus 60 miles per hour for the wind times 180 sine, and I get 502.3. The x component, horizontal component of the resultant, and the y component or the vertical component of the resultant. But we got to get the magnitude of this resultant before we do the direction. You can use a single parallel vertical lines, or you can use double. It don't matter. And remember, the formula for that would be the square root of 230 square plus 502.3 square. And that will give you the resultant, the magnitude of the resultant. So let's do it. Let's do it here on our calculator. Square root it, and I get 552.4 miles per hour. It makes sense. If a plane is going 580 miles this way and is being opposed by wind against it, it's of course going to slow the speed down. It slowed it down from 580 to 552. But what we now need to determine is the actual direction of this plane. Remember the parallelogram? Here's our parallelogram right here. Always both presenting out from the origin. And let's draw a rough image of a parallelogram over here. Our resultant would be somewhere like over here. Maybe this is a little exaggerated. This probably is certainly quite exaggerated because the wind is not going to affect it too much because wind is very weak compared to the plane. But let's get the angle. The angle would be tan theta. Remember, we're doing tan is equal to sine over cosine. The vertical divided by the cosine component. The vertical component divided by the horizontal component. Take the vertical component, 502.3 divided by 230. You get 2.18. So theta is equal to arc tangent of that. I'm getting a 65.39. So theta is equal to 65.39 degrees. So maybe drawing this parallelogram here was not a good idea because I was way off in terms of the angle over here. So 65.39 would be somewhere over here. This right here would be 65.39. 5 more degrees up. The wind has pushed your direction of your plane 5 more degrees this direction. But you got to present the 65.39 in this type of format. And everything is always with regards to the north or with the south. How can we write 65.39? Well, we know the north represents 90. Just minus that 65.39 from 90 and you get 24.6. So our direction, true direction is north 24.6 degrees east. And one of the other reasons why this parallelogram technique in terms of drawing did not appear right, because I didn't draw these things to scale. If I had drawn this all the many times more larger than this, would be presenting or extending, projecting quite beyond this board. And then when you draw the parallelogram, you'd have a very distinct line going up in this direction. So that's one of the reasons why it came out quite exaggerated over here. But anyhow, in terms of calculation, we get a good answer. We get a good answer for the magnitude, and we get a good answer here for our direction. We should do one more of these questions just for practice sake. If supposedly, like in these plane questions, if a plane is going in this direction, P for plane, then we also have wind going in the same direction, helping the plane move on. Of course, the resultant is always obviously increased, so you have an additive effect. But think about it this way: if a plane is going in this direction and it's equally balanced by a much weaker wind, but at least it's in the exact opposite direction, the resultant is still in this direction, but it's decreased because the plane is now fighting the direction of the wind. It's being opposed exactly by the wind in terms of direction, but not necessarily in magnitude. But in the intermediate cases where a plane is in one direction and the wind could be in any other direction, now you have some sort of delicate balance which plays out in terms of the resultant. So you have to keep that in mind, how your resultant would be in terms of the direction. You can have additive effects, you can have cancellation effects, or you can have intermediate effects. So these type of questions are very interesting when it comes to exploring what type of effects you have. So let's present one last scenario. We have a plane which is traveling at a speed of, let's use 500 miles per hour, and it is in the direction of north. Let's come up with 70 degrees east. It is opposed by wind. Let's say it's a strong wind, 80, and that happens to be in a direction north, 10 degrees east. Our goal here is to determine the resultant vector in terms of magnitude and in terms of direction. So we have a plane here at 500 miles per hour traveling at north 70 degrees east, and it is being affected by wind 80 miles per hour but north 10 degrees east. The first thing you want to do here is, in terms of determining the resultant, is always make a graph, because the graph helps you visualize it. Let's do the plane. If it's going, and everything is always with respect to the north and the south axis, but in terms of our final angulations we use 0 or 180 to determine the actual resulting effect. North 70 degrees east means it's 70 degrees from north, so it must be 20 degrees from 0. So my plane is going in this direction, this magnitude with this direction, 20 degrees. I got that from 90 minus 70, so 20. So my plane is 500 miles per hour, the cosine 20 and sine 20. That's the plane. Let's look at the wind next. You know it's pretty routine by now. The wind is going at 80 miles per hour but north 10 degrees east. North but 10 degrees east. That's my wind over here. Of course the arrows are not drawn to scale because this wind arrow must be very short compared to this very long 500. It would be considerably small in size, but we're not using that. We're looking at it mathematically. And that, you know, over here the angle to be 80 degrees. Because you'll do 90 minus 10, you get that 80 degrees. So the plane is at 20 degrees from the horizontal, the wind direction is 80 degrees from the horizontal. Let's write it out in vectors. You have cosine 80 and you have sine 80. All we gotta do now is write these out in their vector broken down components, which we will do. I won't skip steps over here. Plane becomes 500 times cosine 20. 20 cosine times 500. I get 469. Let's not use decimals, let's round everything up. I get 470 for the horizontal component of that plane. Let's do 500 times sine 20. 20 sine times 500. No decimals over here. I'll do 171. That's a vertical component of the plane's vector. Let's do the wind. 80 times cosine 80. 80 cosine times 80. I get 13.89, but I'm rounding that up to 14 because I don't want to use decimals. Sine 80 times 80 for the vertical component. 80 sine times 80. I get 78.78. Let's round it up to 79. So these are the individual horizontal, vertical components for the plane and the wind. You add them up because we're adding the vectors to get the resultant. And you know it's going to make sense. Look, the plane and the wind are in the same direction. You'll have a bit of an additive effect. Let's add these horizontal and the vertical components. 470 plus 14 is 484. 171 plus 79. 171 plus 79 gives me 250. Use that formula for determining the magnitude. You can use 2 or you can use 1. It's all the same. The formula is the square of each added and the square root of that sum. 484 square plus 250 square and square root it and you get 544. You see that I'm getting an additive effect over here. 544 miles per hour. So the plane will have an eventual speed of 544. The wind will help it along. It'll give it a boost to its speed, 544 miles per hour. Our next goal is to determine the angle, theta. We'll put our final answer over here, theta. But what will our theta be? It'll be tan theta, will be the vertical component. Let's say vertical divided by horizontal component. Vertical divided by horizontal component. 250 divided by 484. Inverse tan that. Arctan it. I get 27.3. I get 27.3. Here I'll use a decimal answer, 27.3. But from the horizontal, see, 27.3. But I gotta write that in the proper format, and it has to be with regards to this north axis. So take 27.3 and minus it from 90, plus 90. I did a minus and a plus 90, I get a 62.68. So my final answer will be this. The direction of the plane will be north 62.7 degrees easterly, east. Okay? 27.3 is the same thing as saying north 62.7 degrees east. Because it will be 62.7 degrees east of that north axis, which is 90 degrees, making it 27.3. So here you can see an additive effect. Because the two vectors were in similar directions, so there's an additive effect. If you have both vectors on top of each other in the same direction, you'll have a complete additive effect. In that case, if the wind was exactly in the same direction as the plane, you would have had 500 plus 80, a complete addition. You'd have had 580 miles per hour speed of that plane. So keep that in mind. I like these type of questions because they involve a lot of different techniques. I hope you enjoyed this video. Please like, subscribe and share. Feel free to look at this video several times because I presented many different types of examples. And enjoy your days. Bye.